Welcome back, everybody. Thanks for joining. First of all, I just need to apologize if I sound a little weird today. I'm under the weather, and I probably sound a little bit funky, but I do appreciate you bearing with me. We're going to be continuing with our Chapter 6 notes involving forces, in particular, the force of apparent weight. Now, this can actually take a couple of different forms, or you might say a couple of different notations. And I'll explain those in just a second. Let's pretend for a minute you stand on your bathroom floor on a bathroom scale. Okay? And you obviously have mass, and the mass subject to the Earth's gravity causes you to have weight. And so you have a mass, you have a weight of something, but it's caused by your mass times your gravity. Well, what is reading your weight? What is telling you your weight? Well, the scale. The scale is actually, it's not very vertical, is it? The scale is basically a force meter, and it's applying an upward force. You might call it a normal force. And as the scale does that, the mechanics inside give you a readout of what that force is, and you have a sense of what your weight is. Okay, but you can also think of this as something else. You can think of it as the supporting force. F sup. Okay, it's just another way of writing it. It's like saying whatever force is holding you at your current position. You can also call it the weight force. I'm sorry, I should be more specific, more like your apparent weight. Your weight force is really mg, and according to our notes, like it says right here, you can never really be without weight. You will always have mg. You will always have your mass being acted upon by the acceleration of Earth's gravity. All right, but your apparent weight, that is what can change depending on how much something is supporting you or not supporting you. For example, if you were to jump out of an airplane holding a bathroom scale. Okay, so here's you right here. You got your bathroom scale in your hand. Okay, there's the airplane flying away. All right, and you're free falling right here. And you try to get that bathroom scale underneath your feet. All right, you put it underneath your feet, and you see what the readout is. What will it be? Well, the readout will be 0. The apparent weight equals 0 newtons, or in the English system, it would be pounds. But why? Well, because there's nothing supporting you. Nothing is supporting you. So therefore, your apparent weight is nothing. Does that mean you don't have weight? No, you definitely do. And in fact, you're hurtling towards the ground, and you better do something about it quick, like pull your ripcord. Otherwise, that force is going to be applied to you in a very negative way. But nothing is supporting you. There's no normal force. Nothing is holding you up at a certain position at all. Okay, so we call this the apparent weight. So if you're moving down at the acceleration of gravity, there's nothing to support you, and therefore you will appear to be weightless. That's the whole thrill of jumping out of airplanes, of skydiving, because you feel weightless. Most of our lives, we walk around feeling that weight in our legs and in our bodies and on the bottoms of our feet. Here, jumping out of an airplane, the apparent weight is 0 newtons. But we can also think of it as a supporting force as well. All these are kind of the same way of saying the same thing. In just a minute, we're going to do a problem with a fish. And a fish is on a scale, and the scale is supported from up above right here. So I know in the problem it doesn't actually look like this, but you might have seen these in supermarkets where it's some sort of platform, and it's actually suspended or supported from overhead. And then there's some sort of a chain or a rope right here, and then here's your scale right here. Okay, well, you put the fish or you put whatever produce you want on that, and this force right here that the scale reads is, you might say, the same thing as the normal force being applied to the fish, or the supporting force, or the apparent weight. All these are different ways of saying the exact same thing. Okay? So we're going to see in this next problem now how moving within Earth's acceleration of gravity can affect your apparent weight. I can tell right now this problem having four parts. I might run out of space, but we'll just see how it goes. So, okay. We've got three scenarios here. Scenario one, well, first of all, let me set the background here. We have a fish on a scale in an elevator. Of course, like you always see, right? Well, the purpose of this is, since the elevator can move up and down, it can create different accelerations. Now, in scenario A, it's at rest. Okay, which means the acceleration of that system equals 0 meters per second squared. In part B, we had the elevator moving upwards with an acceleration of 2.5 meters per second squared. Okay, so acceleration equals positive 2.5 meters per second squared. And in part C, we have an acceleration in the downwards direction. That is, the acceleration is negative 3.2 meters per second squared. All right, now in all scenarios right here, this is what's going to be true. We got the fish. Do a better job of that. Make a little more space. Okay, there's a fish, and there's going to be two forces acting on it. Two forces acting on the system. First of all, I cannot draw a straight line up. Come on now. There we go. We can call it the supporting force, which is the same thing as the apparent weight. This is what is connected to the scale, which actually gives us a readout. But we also have this downward force caused by gravity. The fish's mass times gravity. These two forces are both going to be in play in all three of these scenarios. What will change is the supporting force right here. That will change depending on if the the elevator is moving upwards or downwards. So let's try it in part A. Let's see here. Okay, part A. Well, the acceleration of that system equals 0 meters per second squared, which means since the net force on the system equals the mass in question, that is the mass of the fish, which we are told, times the acceleration of the system, well, since that equals 0, then the net force on the system equals 0 newtons. So this is an expression of the net force on the whole system. Mass of the system times the acceleration of the system. However, we can also express the net force as the sum of multiple forces, and we did that just right here a minute ago. We can say that the net force can be expressed as the supporting force. I'm going to write it as, back up here. The apparent weight. It's the same thing. The apparent weight, because that's really what we're asking for right here. We're being asked for the apparent weight minus the force due to gravity, right? Well, if these two things are the same, if they're equal to the same thing, they're both expressions of the net force, we can set them equal to each other then. We can say then that the apparent weight minus the weight force, mg, equals 0 newtons, because there's no acceleration. So therefore, it should be pretty easy to find our apparent weight. The apparent weight equals mg, which is really 5 kilograms times 9.81 meters per second squared. All right. That should give us, I believe, 49.1 newtons. 49.1 newtons. Which, by the way, is the weight of the fish at rest, which makes sense because the system is at rest in part A. All right, so there's no difference between your weight force and the apparent weight in part A because the system is at rest. What's different is when we start having accelerations come into play here. So part B, we're going to have a different apparent weight because we now have an acceleration. Acceleration of the system equals 2.5 meters per second squared. Okay, so the net force on that system can be described as the mass of the fish times the acceleration of the system. And the net force can be described as the apparent weight minus the weight force, right? mg, mass times gravity. So we can set them equal to each other. We can say this. We can say the apparent weight minus mg equals m times the acceleration of that system in this scenario right here. Let's bring the mg over, and I'm going to, well, yeah, I'll do this piecemeal here. The apparent weight is going to be m a cis plus mg. No, what I was going to do is just factor out that m. But for the sake of space, we'll just calculate our apparent weight right here. So that would be 5 kilograms, and I'm also going to cheat a little bit and not write my units in, which I usually want you to do. 5 times 2.5 meters per second squared plus 5 times 9.81 meters per second squared. Mass times acceleration of the system plus mass times gravity. So our apparent weight in part B is going to be, what do you think, more or less than it was at rest? Well, in this scenario, it's going to be more. 61.6. In fact, I'll just write it all in blue. 61.6 newtons. And if you think about that for a second, that should make sense, because if you're in an elevator and it jerks upwards, like it's accelerating upwards, you actually feel slightly heavier. That's what gives you that kind of weird feeling in the pit of your stomach. All right, now let's see what happens when we have a downwards acceleration. So the acceleration of the system is going to be, in part C, negative 3.2 meters per second squared. So we can say the net force on the system is equal to the mass times the acceleration of the system. It's also true that the net force, that is in parts, can be described as, I'm not going to be writing apparent weight in blue anymore. It's just too much to switch back and forth. Heck with it. You know what, I will. In fact, I'll even change the color. Let's make it green. So we can say that the apparent weight minus the weight force, because the object still has weight, is equal to the net force. These two being equal allows us to set them equal to each other. So we can say this. We can say that the apparent weight minus mg equals the mass of the system times the acceleration of the system. Now it's going to look like it's going to work out the exact same way as part B, but we have a different acceleration, so that'll mix us up here. Or that'll give us a different answer. So the apparent weight is going to be mass times the acceleration of the system plus mg, the weight force. Let's do what I was going to do before and factor out the m. So we can say that equals m pull that m out, times acceleration of the system plus acceleration due to gravity. So that means that that's going to be equal to 5.0 kilograms times negative 3.2 plus 9.81 meters per second squared. Sorry, I cheated there a little bit. I didn't put them in for the 3.2, but I was running out of space. So let's see what our apparent weight is now. What is the apparent weight in part C? 5 times the sum of negative 3.2 plus 9.81. 33.1. Let's keep it green here. 33.1 newtons. So this elevator is accelerating downwards. Because it's accelerating downwards, it's providing less supporting force or less apparent weight to the fish. And therefore, that's why it registers a less weight. Now, I'm not going to do part D for us right here. But let's just think about this for a second. How fast must the elevator accelerate, so that the fish is, quote, weightless? That means so that the fish has zero apparent weight. Well, if it's accelerating upwards, that means it's going to have an increased apparent weight. If it accelerates downwards, like right here, it has a decreased apparent weight. So if the elevator is accelerating downwards at the acceleration of gravity, then that means that there is nothing to support you. You're basically in free fall inside an elevator, which is also in free fall. By the way, if an elevator you're in breaks a cable and it starts falling, you're going to be basically feeling weightless inside that elevator until you hit the bottom, and that's a whole other story. Okay? But the elevator must be accelerating downwards at negative, acceleration of the system here has to be negative 9.81 meters per second squared for the apparent weight to equal 0 newtons. So that's part D right there. Part A, B, and C we did together. This right here is going to be kind of a cornerstone to the problems that we're going to be working on towards the end of the chapter. So know how to sum your net force as a system, like right here. Know how to sum it as parts, and then set them equal to each other. And it's just algebra to solve for your problem. So that's it. Example 6.9, the fish scale problem. I'll see you on the next one.